Hi, good morning, and welcome to this ZP webinar on or titling webinar for academics or academia. What we're intending to do here is really just focus on technologies that we've identified as being potentially useful, super useful to academics. I just want to say it's not going to be all talk this morning. I definitely have some hardware in front of me, and I will discuss that shortly. But with that said, let me just go forward and just say, okay, so the focus today is about creating impact. So there will definitely, over the next few years, governments, funding organizations, the Gates Foundation, for example, but also, funders in the US and in Europe and in the UK, etc., will demand impact. So, if they're going to invest public money into academia and its academic research, they will require impact. I will particularly be talking about electrochemical sensors this morning. In fact, I need to grab some sensors now, and I've grabbed them. So I will be talking in particular about electrochemical sensors. If you're not entirely sure what I mean by that, and I'm sure many of you do, this is what the electrochemical sensors look like. And I'll also talk about biosensors. So really that's this kind of, more sort of biological applications. And then also just generally about electroanalytical chemistry. So these terms for me are kind of synonymous with each other. That ZP is kind of well known for biosensors, but that also means that we're actually mostly using electrochemical sensors, and we're also doing a lot of electroanalytical chemistry. And I say here, I'll do a demonstration. So in fact, I will do a demonstration almost immediately, but just to put some real context into this. So let me just change to here for a second. Right, so what I'm going to do is I'm going to do a demonstration because I want to sort of show you what's driving us at ZP. So this is a potentiostat, but it's a very unusual potentiostat because I can actually do, so for example, if I scan this QR code here, I can do square wave voltammetry. If I scan this QR code here, I can do cyclic voltammetry. If I scan this QR code here, linear sweep voltammetry, electrochemical impedance spectroscopy, open circuit potentiometry, and amperometry. Now, what I want to do now is I want to sort of demonstrate to you that when I say creating impact at ZP, we think we've made it much easier to be able to take people from an idea. So, for example, they may be using square wave voltammetry, but to a real world application quite quickly. So I'm just going to try and scan this QR code here if I can, which I have now done. So what I want to do for you is a quick demonstration. So I'm just going to take a real world sample. If you're ever wondering why electrochemistry is such a powerful science, hopefully this sample alone will kind of help to convince you. Look how dirty, brown, full of bits it is. I'm just going to get a pipette, and then I'll do the demonstration itself. So let me do that. Right, so I put the sample on there. I'm just going to name this actually. So let me just name this caffeine. Right, that should have done that. I'll go continue. Now, what this is actually doing square wave voltammetry. But if you really want to translate research out of the laboratory and into the real world, people don't necessarily want to kind of understand that this may be square wave voltammetry, etc. They just want the results really. So what this allows them to do, and that's giving me my result. So I've got I've got a result on the phone, and then actually it's also sent the data to the cloud. So I might just share my screen with you for a second, which I will do here. So I can go in, I can find my data, I can find my device here, and I can see my data up here as well. So it's just to kind of very quickly, and in fact, I can just see the peaks here as well. So it's a very powerful, let's say, back end. This is not something we talk about so much in electrochemistry, but in fact, what we have here is we have two peaks, but you can see the way I can actually separate the two peaks from one another using the back end technology and actually just measure that height and then convert that height into an actual concentration. So peak height becomes a concentration. So what I'm demonstrating here is something called the Sensi-All Potentiostat from Zimmer and Peacock. It's a normal potentiostat, but it's also what they call in the tech industry an MVP, a minimally viable product, that it can actually turn lab ideas into tangible products really quickly. So that was the quick demonstration, and everything else now is in the context of that demonstration, let's say. So at Zimmer Peacock, we're all about translating research into, or academic research into actual products. So I'll describe the current situation, that there's a lot of papers being produced. Everyone's very interested in point of care, point of need testing. People are using screen printed electrodes. I think these are some of the world's best screen printed electrodes. In fact, there's another type that I've got here as well that I'll try and grab as well. They're all rectangulars. Yeah, there we go. So we produce screen printed electrodes, but I think we're really producing some of the world's best screen printed electrodes. And this is really important because I think one of the big problems with electrodes at the moment is they're not reproducible enough, and they're really holding back academic research. But I will cover that point shortly as well. And we'll talk about reproducibility, which I think is really holding things back. I did just show you what's called a cloud-enabled potentiostat. So this is probably the world's, not probably, it is the world's only cloud-enabled potentiostat, where we can make a measurement, send the data immediately to the cloud, process the data in the cloud, and actually send a result also back to the, and I know that's a bit bright, but there we are, and also send a result back to the phone at the same time as well. And no more laptops required, smartphones only, which is an important thing. You notice the way I was using the QR code, I wasn't using menus, I was actually using QR codes. And this is really helping to cross a chasm between, well, you can call it, yeah, crossing a chasm or the valley of death between academia and translation of science. And then I'll just do a quick summary. So the current situation is there are about 25,000 papers per annum being produced in this world of electrochemistry, with a certain title, with a certain introduction, with a certain mechanism. People talk about the chemicals that they use. They'll show some raw data. They then show a calibration curve. So this kind of paper, there are, now this paper, to be fair, is 2008, but there's been a real sort of momentum in these kind of papers, and it's not unique. Let's say this is another paper. I wonder what date this one was produced, but this one's a little bit older as well, but it's the same title, introduction. People have materials. Here they're using screen printed electrodes. Here they have the signal versus concentration and a conclusion. And so there's a sort of a certain structure to these kind of papers, but these papers are not then translating into research. So at ZP, what we're trying to do then is sort of say, okay, first of all, let's identify this, and I wouldn't call it a problem, but let's identify that it's probably about 25,000 papers per annum being produced like this, and they're coming to the market, not coming to the market, they're coming into the literature, but they're not then translating into products. And this is where funders are really going to start having to clamp down soon, because we can't have all these papers and not the taxpayers in the various countries actually not getting a return on investment. So people will want to see more and more work being translated. And that's what we're trying to do at ZP. So what I'm going to do is say that, for example, we took that original paper from Richard Compton, where he was actually doing the analysis of Chile, and actually turned it into let's say, a real product. So let me stop sharing for a second, and let me just go to here, which I'm doing, and just say, okay, so I'm talking about, this is a potentiostat, and I've already kind of demonstrated that we can go from square wave voltammetry, but now I want to go to a different type of analyte. So I don't want to do like academic research. I actually want to now go and do Chile detection, because that's what Richard was doing in that paper. I will take a sensor. I will put it into here. I'll close that up. I'm just kind of grabbing some samples. I don't want to say a little bit randomly, but I realize that it is a little bit randomly. Right. So I may not actually have a sample, let's say, good enough to go. Let me just have a quick look. No, I'm going to take it. I'm going to take a sample, but this will be too concentrated. But I'll do it anyway because it will also show you that we built some intelligence into this system as well. So I've got the system there. I've actually changed analyte quite quickly. I put a sensor on there. I will put a sample on here, which I will now do, and I will go continue. Whoops, a daisy. All right. So I'm just running this, but I'll see if this will actually run because the app is also quite smart. It's set up to kind of be able to make sure that things are in concentration. And it says too high dilutes more, which is fine. But I will show you what that data actually looks like. So I'll share my screen again with you. So I go up to here. I'll go into here. I'll just do a quick refresh, see if another data pops up, which it did just popped up there. And I can see here I can see my voltammetry is very different from the experiment that I just showed earlier on. So you can see that, in fact, we can actually go from amperometry, open circuit potentiometry, EIS, linear sweep voltammetry, square wave voltammetry. If I didn't say open circuit potentiometry, I should say it now. We can do all those techniques, and you can actually use this system to also do analytes as well. And here I was actually doing capsaicin. So we were able to take Richard's original paper and actually turn it into, let's say, a real product. And that translation was actually much easier. I do want to talk about the data pipe that we have at ZP. So the way this system works is we have a very good potentiostat, which works with some very good electrodes, which you can contact us and find these things. We put a sample on there. I use the app to drive the assay. The app drove the assay. The instrument gave the data back. We sent the data to the cloud. We processed it in the cloud, and we actually got let's say, final concentration on the phone. So it's a very powerful data flow built into this system, including smartphones, cloud systems, Bluetooth. It's literally in the gathering of that data, no actual laptops were used. The app that I'm using is actually available on the Google Play Store or on the App Store. They're not much use to you, those apps, unless you've actually got the hardware. But you can see that we've already deployed them. If you do get the app, then you find out that actually what it's doing is it's actually, once you've registered on the app, it's actually opening up an account in the cloud as well. So the app and the cloud are actually synchronized with one another, which is really nice kind of potentiostat, because every time you make a measurement, the data is automatically saved in the cloud, and we can scan different QR codes and drive different types of experiments or even different types of analytes. Now, the only reason that we're able to do all of this is because of actually the screen printed electrodes. There's a problem in the world of screen printed electrodes, that there's this price expectation which is being met by Zimmer and Peacock, being met by others, but what's not being met necessarily is the quality. So there is a problem with quality across the in the world of screen printed electrodes. The problem is that there's more suppliers of screen printed electrodes than there are people who actually need them. So there's more choice than there is demand for it. The problem with all this excess choice is really one of quality. So if you want often a high quality, it's all people say, if you want high quality, you want a high, you have to pay a high price for it. I understand, in the world of consumerism, there's luxury goods which are high cost, but not necessarily high quality. But I think in science and engineering, if you want a good instrument, you pay more for it. If you want something not so good, I've got a balance in this office that's not so good, and I paid a low price for it. So generally, price and quality do go together, and you're a bit disappointed if you're paying a high price and you're not getting quality. But what's happening is actually in world of screen printed electrodes that people are paying want a high quality, but in fact they actually want to pay a low price, and that price expectation is being matched. Now, the only one way you can get high quality and a low price, which is the ideal scenario, is if you have high volume manufacturing. But the problem with this is that you've got Zimmer and Peacock and a good 10, 20 other people doing screen printed electrodes. So we're just one of the problems. And people come and go from this market and they make these screen printed electrodes, and people make screen printed electrodes in their own labs. So you've got lots and lots of suppliers, at least 10 suppliers in the world, all producing something like 50 screen printed electrodes each. So when you look at now at Zimmer and Peacock, actually, we've historically produced a lot of screen printed electrodes, but I would also argue that we're also reducing that these days to just a few of them. So here's some of our screen printed electrodes. Here's some of our screen printed electrodes. Why are we reducing choice? And it's really because if you have a lot of choice, what it means is that the finite requirement for screen printed electrodes is being shared across essentially too many products. So I would argue that you've got 10 vendors producing something like 50 products each, which means there's at least 500 products on the market. And you may have 1 million, a maximum, I would suggest, of 1 million experiments being done in academia per annum. And therefore, 1 million divided by 500 products means that each product is only being sold at volumes of something like 2,000. I'm just going to grab some. See, 2,000 is not many screen printed electrodes. This is a sheet of 300 screen printed electrodes. So I could produce the global demand for some electrodes in 7 sheets. Well, 7 sheets of printed electrodes is barely enough to turn the instrument on. So you've got a problem that people want high quality. They're not getting high quality. They are getting a low price, but they're paying for it because they're fact of the quality. And in order to have high quality at a low price, you need high volume manufacturing. So Zimmer and Peacock, we've actually gone ahead and solved that problem by actually saying, okay, let's not have all this choice. Let's say to people, if you want a carbon electrode, here's a carbon electrode. If you want a platinum electrode, here's a platinum electrode. Here's another flavor of carbon. Here's a flavor of platinum. Here's gold. But rather than, and these are ZP electrodes on the right-hand side here, we can see we produce loads of configurations. But over the years, we realized we're not helping people by having all this choice, because all that's happening is they're all being produced in low volume. So let's actually say, if you want to make a carbon electrode, and I always recommend carbon, use the carbon 501. Just that simple, because then we produce it at high volume, we check the quality of it, and so people get a low price and high quality, and that's something that we've really worked upon. So we are able to meet people on price expectations, and we're able to meet them on quality, because we're actually producing a high volume. And then the other thing on quality is people are looking at screen printed electrodes and sort of thinking of them like glassy carbon electrodes, and so they want to kind of characterize them by the Randall-Sevich equation, or they might want to characterize them by their Nernstian behavior. But when you're talking about translating academic research, real world people, like people measuring caffeine or people measuring capsaicin, they don't care about the Randall-Sevich equation, and they don't care about the Nernstian behavior. They just want to know that the result they get is reliable. And reliability in the world of screen printed electrodes actually relies on reproducibility. And that's the problem, that electrodes are not reproducible. But at ZP, we've really worked on reproducibility. So you saw me do those 2 demos just now. You saw me do no calibration. That's another point about translating academic research, that I make quite simple assays. And the assays are quite simple because actually you see that I didn't do any calibration. The reason I didn't need to do any calibration is because the fundamental electrodes are reproducible for all the reasons I've just mentioned about making sure that we do a few electrodes in high volume means that we get the quality, and part of that quality that people don't really understand is reproducibility. So we do actually have a reproducibility, and we check reproducibility because actually we do a lot of testing in-house and make sure that our relative standard deviation is in the single digits. I think we're the only people who put it out there in the open world what our relative standard deviation is. And you'll see academic papers say, oh, my relative standard deviation is this. But batch after batch after batch, year after year after year, that's really when when you're able to achieve that, that's when you've really kind of got, let's say, reproducibility. And that means that when we're developing assays, actually, we're much quicker and more efficient because, in fact, the underlying electrodes are reproducible. So we're really good at doing assay development at ZP. But it also means that our academic colleagues or people using our electrodes can also rely on our electrodes for reproducibility as well. So the problem that we're really solving at ZP is that people are this is called the Valley of Death. This has been running for at least, I would say, we're in 2025 now, and this has been going for 25 years at least. And I think in part this Valley of Death exists between academia and commercialization because people are using instruments that are R&D instruments. Whereas ZP, we produce a potentiostat that looks like a product. And that means that that gap between what I do in the lab and what I can do in the real world just physically closed because suddenly the instrument is much more translatable. I would suggest that our potentiostat, the Sensei Ore, is more in line with a sort of with an iPhone than it has with a traditional potentiostat. So we're much more on that end of the scale, which is great because real people want beautiful products. They don't want to be using square boxes with the cables coming out of them, just on crocodile clips. So we've really helped the translation through that. So we've done it through something called the Sensei Ore platform. It's really a potentiostat, but it allows people to translate their academic research out of their lab and actually into the real world. Then they can claim impact. If they can claim impact, they can basically get more funding for doing the kind of research that they want to do. So I want to sort of summarize it that at ZP, we support academia through the provision or the sales of very beautiful potentiostats, very reliable screen printed electrodes, and that then means that people can work on their point of care testing with our screen printed electrodes. They can rely on our reproducibility. They get all the benefits of this cloud enabled potentiostat, so they don't have to send laptops out with these instruments, no menus, and then they can commercialize and go from technology readiness level 3 to 9 much easier on. And we think that this kind of instrument should be used in education research. And if you do have any questions regarding this, I would say don't hesitate to reach out to us at ZP. Okay, thanks very much.